Do you want the laser pointer turned on or moving them? No. Okay. All right, sorry.
Okay, awesome. Okay. So, hi everyone. My name is Marc, and I'm from SAP, and we are presenting. Mike. Hi everyone. My name is Marc. I'm from SAP, and we are working here presenting whatever you can do or how you can unlock the potential of your CI/CD when you're generating a lot of high-quality automated data. This was mainly work of our PhD student, Neetha Jambigi, and our student, Marc Türke, but as she is presenting already a different paper in this conference, she's double booked, so I'm presenting it. Goes in? All right. So to give you an idea of the scale of CI/CD at SAP, at least for the SAP Hana database, we are talking here about 50 million lines of C++ code. Complex code, because this is a database system, a very large-scale database system. We have around 1,500 developers working on it, and that means around 88,000 changes per year. So pull requests basically, and we are executing around 800,000 test sessions daily to test the database, to test it for regressions, to test it for performance regressions, and so on and so forth. And this gives us a lot of opportunities when we're talking about machine learning and generative AI. And I would like to make this distinction here because you can do it on static code. Meaning you can do generate for code reviews, you can do it for code generations, as you usually know it, for example, from GitHub Copilot and so on, where you take the source code, you train an AI on the source code to make it generate source code. But there is also, especially if you have a CI/CD system, a different aspect, and that is you can use AI on artifacts of execution. If you do changes to your CI/CD, you get results from test assessment. You got choices for test selection, or you can get fault detection because you don't know what changed. And what we are doing is also fault popularization. So I call it learning on living code, because usually off-the-shelf LLMs are trained on static code, meaning that their main task is code prediction, kinetic token, or if the training task is posed differently, infilling. But anyway, they excel at language tests, as already said. And we want to model the runtime behavior of our software system. We're looking at it as a physical process where you have inputs, and I don't mean the programming inputs, but changes of the CI/CD system are our inputs, and the effects on the software are test logs, are crashes, are build logs, and so on. And these are, in my opinion, essential to model a system, to understand how it behaves, and to model a debugging process, which we then use as use cases, for example, test assessment and fault popularization. Now, the thing is, obviously, we may have 800,000 test sessions a day, but to have good training data, you have to have a very clear relationship between this is my change and this is the effect of it. And authentic data, basically the data you collect from the CI/CD system, is insufficient because usually developers, if they do a change, they change a lot of functions. They touch multiple files. And they often don't know which of those changes had a specific effect, be it a crash or a specific output of a test log on the system. Additionally, there are flaky tests. And for example, if you have old and stable code, this is underrepresented. Not much is happening there, but in future, you might have errors there, but you don't have any training data because it is not being touched by the CI/CD right now. So in the end, even though you have all this data, you don't actually have enough quality data on large language model training. And this is where we generate synthetic data to mutation. So basically, we go in Hana, we modify the code with minimal changes, small mutations, and observe the effects. And you might say, okay, single mutations are not as complex as code changes, but the code mutation literature says this basically first order mutations, so one change has nearly the same effect, or its effect is higher order mutations where you have multiple changes for code. So basically, what we are doing is we are modeling our software as an observable process. We are introducing small changes. We have a process where we generate causes, we observe effects, and this allows us to invert the system. Basically, if we observe specific effects, be it a crash log, be it a test log, we can infer the original cause. This requires that there is a one-to-one relationship between this is our mutation and this is our effect. This is obviously not always the case, but we have observed that 90% of cases this is, and this is sufficient to train the algorithm. And this kind of reversibility of this process gives us the leverage to actually train the LLM and do this prediction. So with that said, basically, just an overview of the mutations that we do. We have a set of mutators which we took from literature. Really small changes like mutating unequals to equals operators, right? Dropping lines, switching numbers. Very ugly changes where you slowly add to the loop bounds one or reduce one to the loop bound, so you already have indirect memory accesses. We do such things. We model different fault behavior, for example, of 100 mutations, 10% of them led to crashes and around 15% to test checks, so basically test errors and so on and so forth. So these are our effects that we are modeling. All right, and so how does the pipeline actually look like? We can find around 11 million possible mutation spots where we modify the code, which led us to around 500,000 of unique crashes. You have to consider that sometimes you mutate the same function with different mutations, but the crash or, for example, the effect test log looks the same. This is a lot of code on build executions that we have to perform, but we are making use of the fact that we can build HANA incrementally, very efficiently, and what I call pre-warm Docker containers. So basically everything is set up to the point where we can start building instantly. So I don't waste any kind of execution process or something that's been already done. And we have something like a graph execution framework, which we use to automate a complete build. And that allows us to only build those parts which are really necessary to have a specific target or unit test or integration test build, which gives us that value. We are collecting all possible information. So, for example, if it did not compile our mutation, we have a build log. If the test failed, we have a test failure log. If the test executed, but the test crashed, we have the crash. So all of these effects and numbers we do have. All right, so I would like to present some things you can do with this data. These are rather exploratory things. Besides fault organization, this is the part where we like invested most of the time, but I will speak the least amount of this because we already have a paper on this on the ICST conference where I would like you to go, where our PhD student, Neetha Jambigi, will present it. This will be on Thursday, I think around 12 o'clock, and it's a session on ML techniques and fault organization in the Grand Hall. So fault organization basically means you get a crash stack, which is a set of frames. I'm showing here SQLite code for obvious reasons, not HANA code, but you can imagine this being actual like software crashes. So you get the crash frames and you want to predict where was the fault which was introduced. And we're not talking about where did it crash. This is sometimes obvious. For example, here it crashed as registered. But this is not the position where we introduce the fault. We introduce the fault in the SQLite 3 malloc function. We modified, for example, the pointer reference. And this results in a crash somewhere else. And we use this, we do a lot of mutations, we have the crash tags, and we want to predict the file and the function name where a fault was introduced. And this is the typical use case for fault optimization if you start off. And as a use case, we are helping our developers kickstart the debugging session. If you get a crash and you don't know the code because maybe this is something you didn't work on, you know, oh, actually this is this component, this folder, maybe even that file, which has a fault introduced where I can start debugging and see what the problem is. Also, for example, using this as a topic extractor, if you have a lot of test executions, very different crashes, You can cluster them using typical approaches, be it like appending with CFIDF or BERT or something else in cluster risk, but you can also extract the root causes and the fault locations and cluster problems that way. So if we do that, if we train a large language model, here in this use case, we train Center Code or Mistral or Microsoft Phi, doesn't matter. We are data constrained, all the LLMs work the same way. We get an accuracy of around 60%. And can say, okay, if you change something here, the likely location will be there. More info on this topic, as I said, in Neetha's talk. Okay, what else can you do if you have this data? So basically, all the use cases I'm presenting is the same data, only the way you turn it around. If you have executions and diffs and changes, and you have the tests which you execute, you can do something else. You can predict which test is going to crash. So for example, you know, okay, I did my mutations here and there, and if I execute a test, this test crashed. So again, you have a use case where you have a diff, you have a final function name, and you're predicting a specific test. This is useful, obviously, for test prioritization or test selection. Again, same here, we are training the large language model using the diff and making it predict the change. What you will see here is that if you don't give the classifier any consequence, it will instantly overfit. We had accuracies of around 80%, but after investigating this a little bit, the point is it follows coverage very closely. So if you have line-based coverage and you know that these tests actually cover that lines, our LM basically learned the same thing, but a different way. So what you have to do is a little bit of stratification, meaning we try to predict, for example, which test is going to crash without actually showing the previous crashes in the same function, nor actually the function name. So basically only on the changed code. The point here is being to understand what changes to what classes, to what functions will lead to for some specific tests crashing. And in that case, we can predict the crashing test with accuracy of 25%. Interesting, the large language model and the random forest actually have the same accuracy. And that means basically that we are not extracting structure, but we are extracting unstructured data, meaning that it's very likely that the main information contained here is the actual class name, function names, and variable names, which each define. Yep.
Oh, just very quickly, what was the input for the prediction here? Is it the diff?
Yep.
Okay, so okay, sorry, I was like, my context really wasn't figured out that. Sorry.
Okay. All good. So fault organization and the test prediction was the diff, and the next use case will switch us around.
Okay.
Anyway, so you can get around 25% if you want to be test case specific, 50% if you want to be test target specific. All right, crash text prediction. We switch around. No, actually, still a diff. I'm sorry. It's still a diff. We go by the change, but we are now not predicting actually what is going to crash, but the crash itself. So basically, how is a likely crash is going to look like if I change this? So this is some kind of a priori information. This is not bug detection. Basically, I'm just saying if it's a crash or not. No, we know it's going to crash. The question is, how is the crash going to look like? We give it a change diff, define a function name, and to predict the crash. What is useful for first test assessment? If you know that it crashed, you can see, is the crash which I got actually a likely crash from my change? Then I can detect, is it an infrastructure issue, or is it really from the change which has been given? As a possible review tool, for example, you modify code and you instantly get a feedback. Okay, what is the likely effect of my modification? Is the crash which the LLM predicts realistic? Is it something I expect, or did I suddenly or inadvertently modify something which I didn't predict the effects of, right? And it's a little bit useful for the fault localization, because the fault localization is very singular. You give it a crash and it says, okay, it's here. That's not a lot of information. We want to have some kind of justification with reasoning. And what we here can do is that we can look at our fault location position, go through all last 10 changes at that point and see what kind of crashes that might have generated and say, okay, this change in your CI has likely led to a crash which you are now seeing. This is a little bit more justification for the developers. And we also encode the knowledge of the fault behavior in the large language model. We can transfer this knowledge to junior developers. For example, if you modify that code, you will make crashes which will have this. Right? So how we are measuring? We are looking, we cannot expect the LLM to generate crashes which are identical, right? So, because, for example, the test frames might be different and so on. We are expecting that matching subsequence is there present, and we do the mean average of all matching subsequences, and for example, we can get an accuracy of 50%, basically, that in most cases, half of the crash stacks is well predicted. Okay, what does it mean to predict a crash stack if you have a function? What may happen is, for example, if you have a single function, it will have different modes. I mean it in a statistical sense, different clusters of crashes, basically because you use this function in different contexts and different code paths flow through it. So if you modify something, you have some crashes in that part of code, some crashes in other part of code. And here, for example, we see the similarity matrix of all generated crashes. We use cosine similarity and TF-IDF to do the clustering, but basically we see here two modes. Blue means crashes are dissimilar, red means crashes are similar. Point being is our LLM is able to predict the modes, it's able to predict the correct modes, the correct cluster group for a given change. That's obviously not always the case. So there might be functions, like for example, here this session is any logarithm. On the rightmost side, you see a triangular matrix, all blue, meaning very, very many dissimilar crashes. We are not able to model it. Because if you look a little bit to the right, that one, the prediction shows different ones, but so this is true, this is prediction, and dissimilar ones because we are not able to model all possible paths of code which flow through. But that might be an effect, for example, because our LLM is too small. For different functions, where all crashes are similar, okay, that one is easy. But even the one which I have shown before here, for example, the pattern that we still execute, where we, in the test cell, had two different modes. In the training set, we had actually very many different crash clusters. And still, we were able to predict, okay, to say, for example, for that change, we will get these crashes, and so on. All right, different use cases. In summary, what I want to say, if you mutate your code, if you have the ICST, which generates effects, basically. If you look at it, it's a physical system, right? You get changes in, you get effects, be it executions, build blocks, crashes out. You can model it with generative AI. And you have many different use cases you can use it in different ways. There are some limitations, obviously. First, the preliminary results. We only use first-order limitations. What I show you, the results are all in synthetic data. So basically on the data we generate ourselves. Running this on authentic data, it is quite hard because you have to know which authentic data you are trusting. And we are currently only thinking about productizing for productization. Okay, thank you very much. I already see the perspective.
You said it was hard to know what authentic data you can trust. What does that mean?
You have like test executions. So for example, you have crashes or test which will crash when you execute this. There's no easy way to protect that. That I know, for example, this execution that was breaking. You have 20 functions changed. Only one of those had actually the effect of this crash. I don't know which one of those 20 changes it was. You have infrastructure errors, for example, connection errors. Was the connection error because there's a bug in the code, or is the connection error because of host testing? I don't know. That's the problem.
Right. How did you embed the diff? So how did you feed that to the LLM?
You know, we are fine-tuning, we are training our own large language model. This is a simple prediction task. We're predicting the next token. So basically, this is the prompt which the LLM gets, and it ought to predict the tokens which you see in the answer. It's really text concatenated and will then be predicted as a next token prediction. Yep.
So, what's the cost of this, like, fine tuning? Like, you could generate a lot of data through mutation testing. I mean, like, how much do you really have to do to get the accuracy numbers you're talking about?
Yeah. So
how big of a model do you have to use? Can you do this on like something small, or do you need like a lot of parameters?
the semi-program model used here is a 1 billion model, but we have better results with Microsoft V, which is a 13 billion model. And the funny thing is about a large language model training, the training is cheaper than inference because you're training with complete batches. Like you don't do this generated decoding where you find the LLM for each token. You can train, for example, this complete example can be trained in one go. So the costs for the training are not that big actually. And 500,000 examples is not much in LLM training.
Okay, so yeah, but you could keep making more.
Yeah, the infrastructure costs are actually larger than the actual LLM costs.
Okay.
Speaking of this,
Yeah, but you just deny the desk. You don't actually have to
Oh,
calm down.
got it.
Just
Got it.
stand up straight.
Yeah, so for one of your earlier use cases, you showed this comparison to the random forest. I'm curious if for your other use cases, are you finding a similar pattern that the performance is fairly similar between like tree models and LLMs?
Yes, so for the question prediction is not going to work because it's truly a generative task because we have to generate a crash stack, and there's no way you can classify this. For the fourth localization, we can do that. And we see that the random forest around 10 to 20 percentage points grows actually. So here the structure of the crash stack is relevant. Only the test prediction case it wasn't, or it surprised us, but then we thought, okay, it's very likely that our model is simply modeling the frequencies of specific words.
Yeah. And then I guess secondary question. So yeah, you mentioned that it's hard to sort of test this on real data. I guess I'm very curious about that correlation. Have you looked into it at least to see, well, you know, your LLM that's fine-tuned on your mutation data, how well does it perform?
So we achieve here around 60 to 70% accuracy with authentic data between 30 and 40%.
Okay.
But then the question is, how much do you trust it? We're very optimistic in extracting it. So are we actually over predicting, or we're very pessimistic in extracting it? So actually, are we worse? I don't know that.
We have minutes, so I'm going to ask another one. I know this was done by your PhD student, not by you guys, but did you compare against the discriminative subsequence finding approaches that were popular for stack trace-based fault localization in, say, the 2010s? Some very good work. I actually replicated the work, so I know it was good. Yeah.
So I know that we did not compare against it, but I can't comment any more on that. I would know more. I would invite you to go on Thursday and ask her.
Yeah, the downside of the discriminative mining. So discriminative mining, you take like passing and failing runs, and you find what discriminates between them. So it's actually quite powerful to find the most important nodes in your execution choices. But the downside of such approaches is you do need the test input because you need to be able to actually execute the test. Whereas you can take an operational failure, where you just have a stack trace. So that's an advantage.
This was actually our main use case. Basically, we are looking at if you have a HANA database in production at a customer, you only get a crash. What can we do with that? What can we train in a model? What kind of information can we collect that? If we just get a crash stack, can we at least point it to right direction?
You mentioned that it's an issue that you do not have kind of these atomic changes that have direct cause relation, right? When you did the evaluation, and this is why you did the mutations, right? When you did the evaluation, did you do that on the mutations or on the kind of real world large changes?
This evaluation we did on the synthetic, so basically the mutations, not on the authentic. Because the authentic data is, like I said, it's hard to know. I can show something basically, but I don't myself kind of trust it that much.
Thanks.
Okay, last question. I'll cut myself off. This is good, actually. But did you try taking a static trace and generating a test case input?
No.
Okay, because you could try and generate reproduction for debugging purposes.
Oh yeah, new testing. That's a good idea.
You should do that. All right, next year, ICST, look forward to your presentation on witness, test witness.
That's good.
Yes.
Thank you.
Witness the yellow letter. There's a big okay. All right. And then we have arrived at our last paper, or not paper, but presentation, discussion. Come on forward. And we will, after this, be then going to coffee break. And then please do return to come and chat with us about problems in CI/CD. And then we'll do open steering committee. Okay. As I'm pulling up the slides, Martin, have you made dinner reservation?
Not yet.